Namaste, everyone. Welcome to the Transitional Artificial Intelligence Group Seminar Series. This week we have Mahsa Tavakoli from the University of Western Ontario. Mahsa has been part of our group, and I have been her external supervisor from last year. Mahsa is working in the area of machine learning and deep learning and applying it to finance and economics problems. And today her talk is about multimodal models for credit rating prediction. Mahsa, you can begin.
Thank you so much. My presentation today is about multimodal models for credit rating prediction. So we are going through a motivation, research questions, methodology, dataset, prediction, and finally conclusion. So the motivation for research is the fact that knowing the factors that play a significant role in credit rating leads to better decision-making in financial applications. The main focus has been on structured data, and fewer studies have addressed unstructured data such as text, video, images, or even multimodal data set. Financial applications so involves various types of data sets, which required various techniques for the field of information fusion to this interaction. The research question will be mainly 4 research questions. The first one will be the fact that which combination of fusion type, order, or strategy, which I then explain what is the difference between fusion type and order or fusion strategy. And deep learning models such as CNN, LSTM, GRU, and BERT leads to better performance for application of credit rating prediction. The second question is that what is the contribution of each modality separately, and which channel plays the most important role? The third question is that how much is the model reliable during an unexpected crisis such as COVID-19 pandemic? And the last one is that what is the impact of different rating agencies on short-term, medium, and long-term performance? About background, because we use transformers here, I just briefly explain about transformers. So the transformers network is based on attention mechanism. The self-attention mechanism basically allows each part of the data to attend to all of its positions. There are 3 vectors of query, key, and value from the same sequence of data, which they will connect, and they will connect to the encoder and decoder. About self-attention, query and key will be matched to calculate the relationship to each other. Value represent the information to be extracted from the input embeddings. So there are 3 vectors that are packed into matrix of Q, K, and V. To allow computation of this attention to generate this output as attention scores. So the goal of this is creating this attention score. This is for self-attention. However, we have cross-attention. So cross-attention has been used to replace concatenation and improve the fusion performance over multimodality data. So the mechanism is almost the same as self-attention. However, the difference is that it uses query and value from the sequence of one modality and key from the other modality. So the only difference is in this part. And such mechanism is really useful and helpful that leads to identify the correlation and interaction of different kinds of modality of datasets when combining them together. About methodology that we used in this paper. So here first, I explain briefly about fusion strategies that I used in this paper. So mainly there are 3 fusion levels. The first one is signal or early level fusion, which is this one that combines raw data directly. And these preserve maximum information. About the second one, which is intermediate level fusion, which is here, this image, this merges information from different layers after feature extraction. So here we have raw data, and then there is layer 1, layer 2, and after this layer, we can match and fuse these kinds of information. So this is intermediate fusion. The last one is late or decision level fusion, which they fuse information after having output. It can include decision or prediction output from previous models. So this lies in this image. What about hybrid fusion approach? So hybrid fusion approach is combination of various fusion levels. For example, in this presentation, we use early and intermediate fusion in order to have a hybrid fusion approach. But another example can be early and late fusion, for example. So these kinds of approach leverage the strengths of multiple fusion strategies, which enhance performance and robustness of the model. So generally, the methodology will be a combination of deep learning models, the well-known deep learning models, and fusion techniques. So here we have 3 things. The first one is deep learning models, which here in this presentation, we use CNN, LSTM, GRU, and BERT. The second one is fusion levels, which as fusion levels, we use simple fusion levels and hybrid fusion levels. And then about fusion strategies, we use concatenation and cross-attention. So we are going to combine all of this information in order to make some models to predict credit rating. So our models basically are in 4 categories, in 4 main categories, or 4 main groups. So the proposed model in group 1 is simple concatenation. It means that we have 4 kinds of numerical data set that in the next slide, I will explain that what is exactly each of these. But these 4 information or modality are numerical information, which this information passes through a network, such as network A, and text information feed to network B. And then output of these layers will concatenate to each other. So this group is a simple concatenation. Network A and network B is in this way, which we have some base model. For example, our first base model is CNN, which is here is 2 convolutional layers, dropout, global average. The second base model is based on LSTM, the third one GRU, and the last one is based on attention mechanism. So this group 1 has 4 subgroups, basically. But what is group 2? Group 2 is simple concatenation attention. It means that here, for numerical modalities, channel, after passing through network A, we concatenate all of the information of numerical, and then we feed text to network B, And after that, we use cross-attention to merge the information of numerical and information from text. So here, because we use two fusion strategy, here the name is concatenation and attention. The next one is group 3, which here we use basically hybrid concatenation. So what is different between hybrid and simple? Here, the difference is that we use early concatenation and then intermediate concatenation. So because we use two different levels or orders, then this one is hybrid. And because both of them is used concatenation, so the group name is hybrid concatenation. About last group, we use hybrid concatenation attention, which is the most complex one. So here we concatenate all of the information from numerical channels as early fusion strategy, and then after we pass text through network B, then we use intermediate fusion strategy, and as a strategy, we use cross-attention, not concatenation. So here we have hybrid concatenation and at cross-attention. So what is dataset? Basically here, our target data is rating, credit rating. Credit rating is that we use is based on 3 types, which is the most well-known one. For example, Moody's, Fitch, and S&P, which each of them can be matched to some numbers or code. So generally, we have 22 codes or classes for credit rating. Class 1 refers to the highest quality, and the last class, which is class 22, refers to the defaulted company. And because this is our data set here, which as you can see, in some classes, we have enough and sufficient data set, which is fine. But there are some classes that we don't have sufficient data set. So we matched some of these classes to each other. So our new classes is in this way. That our new classes are 8 categories instead of 22. And here is the frequency in each classes that as you can see, it looks sufficient. What about numerical channels? Our numerical channels collected from 2010 to 2022. There are 4 types of information. We use bond information. So there are 8 features in bond information related to securities such as high price, low price, trading volume, and so on. There are financial ratios, which is 45 features related to financial ratios of companies, such as, for example, valuation, capitalization, liquidity, efficiency ratios, something like this. And there are market data set, which is 98 features containing market features. For example, monthly index built on market capitalization, index on S&P, monthly stock market, US Treasury and inflation indexes. And the last one is covariate features, which contains rating agency type and also the last rating classes. But what is text? What is text? So we use earning call transcript. The earning call transcript is like a periodic conference by executives of companies in order to compile companies' performance. The main source is here in this website that we extracted and crawled the text from this website. But there are some examples of the document, for example, here as you can see. So here is result about text visualization. So this is the frequency of our text. This is frequency. This is, for example, the number of words in each document, which is from 50 to 10,000 words. But the most frequent one are with almost 5,000 words. About number of words in each classes. As I said before, we have 8 categories or 8 classes in terms of credit rating. And number of words in each classes is almost 5,000 in each class. Because we wanted to visualize our text document, we separate the classes and the rating into 2 main groups, high rank groups and low rank groups. High rank group refers to the classes with high quality. The low rank group is classes with low quality in terms of credit rating. So in high rank document, the well-known word is really, for example, growth, kind, well, and this is the most frequent word in low-rank documents, like quarter, million, and well. But the more useful figures is this one, which is 1 gram, that shows the most frequent word in high rank or group 1, which is this one. That does not include the most frequent ones in the low ranks or group 2. So as you can see, the range of common word in high rating document is more than low rating group. And another difference is that in high rating document, which is this one, the common word contains adverb, such as obviously, actually, but the common word in group 2 contains more verb. For example, or even there is a negative verb such as don't here, which we don't have in group 1. Also, we have bigram figures in order to figure out more differences between these 2 groups. So in group 1, the most common combinations such as text rate, next year, second half, and these kinds of word is the most repeated word. And in group 2, which is a low rank document, is different, like this: approximately million, prior year, would like, free cash, like this. But what is model prediction? First, we introduce some evaluation metrics. So we use AUC and F1 score. We use these 2 metrics because we have unbalanced classes. So these 2 are the most appropriate metrics for unbalanced classes. And this is our table and result. So we train each model in a way that each one reach its optimum performance. And also we present the performance within 90% confidence interval using bootstrap technique. So as you can see, these are our 4 groups. that I explained in the previous slides. And also these are our base model, which was CNN-based model, LSTM-based model, GRU-based model, and attention-based model. So as you can see in each group, the CNN-based model performed better compared to the others. And CNN-based model in group 3 outperform others. But what is CNN-based model in group 3? So group 3 was in this way, that here we used concatenation as hybrid fusion strategy. So we use concatenation in early level and intermediate level. And network A and B are based on CNN models. So this is the exact architecture of our models, our best model, which, as you can see, there are contains of several convolution, dropouts, max pooling, and global average for both of numerics and text. And then we concat, then we use flatten, dense, dropout, and then we have our output. So here is our convergence plot. And here is the confusion matrix. So from the last table, we can say that the performance of the transformer-based model as a state-of-art model is not the most. The reason may be because of the limitation of accepting tokens. The second point is that the transformer-based model perform better when the fusion strategy is cross-attention instead of simple concatenation. And when each channel separately trains and then cross-attention is applied. So the next point is that when we use cross-attention fusion technique, models' performances become close to each other compared to concatenation techniques. And the last one is that although both LSTM and GRU are kind of RNN, and performance of GRU is much better, performance of GRU is much better in this specific application. The reason may be because GRU is a simple model, and in our case, maybe the dataset is not too large or too complex, and GRU is sufficient for this application in compared to LSTM. In this slide, we applied two kinds of robustness tests, out of time and out of universe. So out of time is the way that the train and test data is split based on time index. Out of universe apply and measure the performance of out of universe performance of out of universe robustness is obtained so that the test set contains the corporates which were not in the train set. So as you can see here, the performance of both out of time and out of universe is almost the same as our model that we saw before in the previous table. About the role of each modality in prediction. So here we separate each modalities and apply the model for each modalities. As you can see here, the performance of text channel for base model is 92% in terms of AUC. However, the performance of numerical channel in terms of AUC is like 80% for covariate, 79% for financial ratio, 77% for bonds, lastly 53% for market, which indicates that text information contribute the most. However, market information, market contribution is not really good in this application. In this slide, we want to investigate effect of COVID-19 on models performance. So here we have performance of our model before COVID-19 and performance of our model during and after COVID-19. So as we can see, the performance during and after COVID-19 is higher and better than the performance before COVID-19. So the reason may be because after the crisis, many predictable trends and structure gained less credibility. And for example, most of the previous models were mainly focused on numerical data. But the role of oral and text record became stronger than before in affecting corporate credit rating. And as we can see in previous slides, the role of text data was prominent, and it can be expected that the performance during and after COVID-19 increased. And in this slide, the result is based on type of agencies and lack of prediction. So in general, we saw that from the previous tables, we saw that the performance of course, I don't have table here, but I can explain from the figure. The performance of rating based on MR or Moody's is the highest. So the blue one is performance based on Moody's. As you can see, is the highest. So we can say that the Moody's agency rating is more predictable than the other types of agencies. And if we combine the result of agency type with the lag, medium-term prediction based on MR agency outperforms. So this may be because we know that the text contributes more than numerical data. So it does not seem unrealistic that the impact of transcript and text becomes more apparent over a longer period, depending on the agency type rating of target data. So we can expect that this happened. Medium term outperform short term, for example, because of the contribution of text data in this application. And we have future work, which is we can incorporate Bayesian models. We can implement data augmentation, for example, address class imbalance with data augmentation technique, or improve model generalization and predictive performance. And also we can apply framework for country-based credit rating prediction. So this was my presentation today. If you have any questions, please ask.
Thank you, Mahsa, for an excellent presentation. Any questions from fellow attending it? Okay, I have a question. Can you give some more details of the future works, what you are engaged in now?
Yes, so again, I'm going to share my screen. It was future work?
Yeah.
Which part?
The current paper you are working on, the Netherlands. Can you give details?
Oh, yes, for sure. In the current work that I am working now is about prediction of mortgage risk based on various information. For example, we have some maps, images, and we have some news categories. So in my work, we focus only on unstructured data set. And we extract some kinds of like sentiment scores, which is kinds of structured information out of the news. So we have three types of information: news, maps, and sentiment score as numeric kinds of information. Then we combine these kinds of information in order to predict mortgage risk.
All right, that's interesting. Any other questions do we have from the team? Any comments, questions? The other thing, Mahsa, could you give some details about your GitHub repo for people, the code, what type of
So I have a link here for my...
Yeah. If you could open that up, that would be great. Give a bit of a overview of where is what, about the data set. Is the data set in the repo?
Because this is my course basically. So here I explained that, for example, what is each group, and then we have code here that this is separated based on groups. There are codes based on the group, but because the data set is secured and we don't have any permission for releasing these kinds of data set, I don't have any kinds of data. I just explain about the numerical features that we use in this paper, but I don't have permission for that to put here in this GitHub.
Okay. And what did you use to run the code? Like how much of computational time did it take to run one model?
For example, I had 16 models there, but for running one model, it depends on the model. For CNN models, with supercomputer, it took for me, for example, 2 or 3 hours for each model. But when my model was based on transformers, such as BERT model or combination of BERT model or cross-attention, which was the most complex one, it took around like 7 hours or 8 hours for each model.
Does your results report multiple experimental runs? Like how many experiments you did? You did single experiments or 30 experiments for each case?
Basically, because as I said, I had 16 models, and for each model, I try to reach each model to its best and optimal performance. So for each model, I approximately tried, for example, a lot of parameters, learning rate, or some. I think for each model, it took 20 or 30 times experiment for me for each model, and I had 16 models.
Okay. Anything else? Anybody? All right. Then thanks for excellent presentation.
Thank you so much for your attention.
Okay. Bye-bye. Thanks, everyone.